All right, so this is in the little added packet because we have notes in the other packet on normal distribution, and we will talk about those again on Friday. Tomorrow is a really weird day, remember, and so half of you won't be here, so tomorrow's basically going to be a work day for those of you who are here, okay? If you need to know whether you're here or not, you can ask me later. All right. So the idea today is that certain things are what's called normally distributed, which is this, like a lot of people call the bell curve idea, okay? And sometimes we make assumptions about data and it being normally distributed, and it's not necessarily true. But when there is data that is normally distributed, we are going to start with what's called the empirical rule by assuming things are certain standard deviations away from the mean. Does everybody remember we talked about mean? It's just the average of the data points, okay? And standard deviation is how spread out the data points are. Okay, one standard deviation either way from the mean is going to be this set of data here. We're going to call that 68% and so on. I don't know if this has any valuable information if I make it a little bit bigger, because it certainly doesn't at this size. Not a lot. We're good. The idea is just that this shows data can be normally distributed even if it's not all the same. Oh, we get to talk a little bit about when data is not normally distributed, okay? Let me remember what exactly I called this first one. Yeah, that would mean it. So the first one is called right skewed, when all of the data is to the left and the tail is dragged off to the right there. It's also called positively skewed. Who has AP stats? Do you use one over the other, Maddie? Like for this, would you call this right skewed or positively skewed? Okay. Okay, this is how I remember it. Like, it's screwed up on the right. There's hardly any data over here, okay? The tail, if you were to draw the little tail like this, it's trailing over on the right. And this is left skewed or negatively skewed. And this is called symmetric or normally distributed. What positive or right skew means is that the median and the mode are over to the left of the mean, okay? So the average would be somewhere in here. The highest bar is clearly the most often occurring answer. Does that make sense, guys? Okay. So here, when you averaged all these, the average would be somewhere in here, but the mode is over here somewhere. When it's normally distributed, the mode, median, mean are all roughly close together, okay? They'd be perfectly together if it's perfectly normally distributed. If you averaged all of this left skewed data, the mode is clearly further to the right than wherever the median and the mean would be. Okay, not something I'm going to ask necessarily on a quiz. All right. Normal distribution is asymmetrical, and we use the word bell-shaped curve defined by the mean and the standard deviation of the data set. The area underneath that curve represents the probability. With the total area equal to 1, all the possible probabilities. So we're going to do a whole bunch of examples, but if I scored you, and I said I was gonna take your quiz, if I scored it as percentages, and I said I was gonna normally distribute them, okay? That means that most of you, I would give most of you in here a C, a few Ds, and very few Fs. And up here, you'd have a few Bs. I'm sorry, yeah, this is not, it's not even, so. And some A's. Has anybody ever had a teacher say, I'm gonna curve the grade? Okay. It's kind of disturbing to me when they do that because it means only a couple people can get a really good grade. So the top couple people are gonna get the best grade in the class, and it doesn't matter how good or bad that was against the whole thing. There are times when it's appropriate, okay? Another thing normal distribution is used for, and we'll talk about this on Friday, is if you want to compare normed tests include things like the SAT and the ACT. If you wanted to compare your score on one, your cousin took the ACT and you took the SAT, and you want to know who really got a better score, okay? You could say, how far above the average are you? How many standard deviations above the average was my score versus their score? That's a way we can compare things that are norms like that. All right, I'm not making very good examples today, but all right, so this is what's called the empirical rule, and it's a rough estimate. It's pretty close, but it's an estimate that we use to memorize when things fall on exactly standard deviations, one side or the other, okay? So the mean is in the middle, and then we have 34% on either side within one standard deviation. So one standard deviation below, one standard deviation above. Then the next is called, this is 95% of the data within two standard deviations. And it's 68 in here, and then the other 27 is split here and here. Okay, so this empirical rule is sometimes called the 68, 95, 99.7 rule, because the rule is when you go out 3 standard deviations, you've hit 99.7%. Okay, you have this on your reference sheet that I gave you today. So we're gonna write in our notes, okay? Approximately 68% of the data falls within one mean, 95% falls within two means, and about 99.7 falls within within 3 standard deviations, I'm saying it wrong, of the mean. Okay, so this is the mean, and then this is 1 standard deviation below and above, that would be the 68%, or 34 on this side and 34 on this side. All right, and then it's 95 here within 2 standard deviations, which means this adds 13.5 and 13.5. And then it's 3 standard deviations, covers 99.7. So does your table say 2.35, the one on the reference sheet, guys, in this little spot right here? Okay. This notes sheet is from an author that used different numbers, and I went on the internet and I was like, these are the numbers I learned and these are the numbers that I've always seen. Hers were just a little bit more specific, and it was kind of miserable. Everybody got what they want? It'll make a little more sense when we do an example here. All right, so we are going to draw and label, and you do have to do that on the quiz for one question. It says the weights of the 50 football players are normally distributed with a mean of 178 pounds. So in the middle here, we're going to label 178 pounds as the mean or the average. a standard deviation of 8 pounds. We're going to keep adding 8 going up and subtracting 8 going down for each of these lines. So adding 8 would give us what? 186. Thank you. Adding 8 more would be 192. Did I do that right? 4? No, I didn't. 194. And 8 more would be what? 202? Somebody help me. Okay, going down, I can do the first one, 178, 162. Yeah, 170, I wrote it, sorry. 178 was the mean, 170, 162, and minus 8 more would be 156, 54. Subtracting is not my thing, guys, we know this. Thank you. All right. And so again, this was the mean, and 8 was one standard deviation. That's that goofy Greek letter, okay? And it goes 34, 34. I'm just going to label one side here, 13.5. And what did we call this one? 2.35? Okay. What is the percent of players between 178 and 194, guys? So if this was a quiz question, I actually have one where I ask you to shade that area. So you would shade this area in here for question A, okay? And then you would just add up the 34 and 13.5 and say that is 47.5%, because it asked for percent. What is the probability that a player weighs at most 170 pounds? Okay, at most is 170 or less, right? At most. So we want to know this going this way. Now, it would be a very rough estimate if we just added 13.5 plus 2.35, but there's actually a little bit left over down in here. Generally, what we do in this situation, okay, let me do a different color here. So we're talking about all of this. We say this half was what percent, guys? What's the mean? 50%. And then if we take off what we didn't shade of that half, the 34, that leaves 16% below that. So it was the lower half minus the first standard deviation, and we left shaded 16%. If we had added up 2.35 plus 13.5, it adds up to 15.85 or something. It leaves this little piece down here, okay? What is the probability that a player, and you can answer as a percent or a decimal. In Delta Math, they'll specify what they want. What is the probability the player weighs less than 162 pounds or greater than 194 pounds? So if I were shading this in yellow, I'd have these guys and these guys, right? Anybody think about how we could best do that? Yep. I think that's the best bet because we didn't really have a number out on these little tippy ends here. So, I think it's 5%, isn't it? Because it's from here. Are they even? Yes. So remember, one standard deviation was 68%, guys. 2 standard deviations was 95%. So you could subtract 13.5 and 34 and 34 and 13.5, but it's supposed to be 95 in there. So it should be 5% or 0.05 or 5/100ths. Or... how much the tip is? Yes, yes. I think it uses 0.1 roughly. But, all right, how many players weigh between 170 and 186? Now, this is a different question. We're going to find a percent over here, but then it actually says how many players. We have to read really careful. So between 170 and 186 was just the 68%, guys. Everybody see what I'm talking about there? So 68%, but that's not of the players, of 50 players. Good job. Samantha said of 50 because there were 50 players here. So 68% of 50, somebody? I'm thinking 34. I'm not going to be super picky. If it's a decimal, 5 or above, round up, don't round down. I'm not going to be picky about that. All right, let's try number 2. Can you go through and label these? A set of 120 test scores are normally distributed with the mean, which goes here, of 82. Oh, and a standard deviation of 5. I think I can add 5s. So we add 5s going up, and we subtract 5s going down. Okay, so this is 1 standard deviation either way, or 68%, 95%, 99.7, or you could do the 34, 13.5, 2.35. Okay, you have the reference sheet for the quiz. All right, what percent of the scores are between 72 and 87? So if I had asked you to shade, it would be these 3. So what are we going to add up, guys? Is Jada the only one who's getting this? I know you people. Everybody okay? I know you guys are just so quiet, but we had 34, 34, and 13.5, or 68 plus 13.5 is, what is that? 8, 9, 10, 11, 81.5? Did I do that right? All right, what is the probability? This one said specifically percent. This says probability. You can answer as a percent or decimal. What is the probability that the score is greater than 77? Okay, rather than add all these up, what's this half, guys? Greater than 82 is what? 50%. Plus all the way down to 77 is here, so that's a 34. So that would be 84%, or 0.84, or however they asked for the probability in Delta Math. Right. What is the probability that a score is less than 82 or greater than 92? So less than 82, well, less than 82 is what? 50%. But it also works if it happens to be greater than 92. So we could do what? Yeah, I would do 100 minus those other 2 probably, since this is all the way up. Whoops, that's not right in yellow. 100 minus 13.5 and 34. Let's see, that would be 47.5, 52.5? What is it, guys? Thank you. Right, about how many students, this time we want students, scored outside 2 standard deviations of the mean? Okay, so what's the rule? 2 standard deviations is what percent, guys? What's the empirical rule say? 95%. So what does that leave? If 95% is within 2, then 5% is outside of that. All right, and it's how many students, so we have to do 5% of what? Yep, of 120 students. So 0.05 times 120. or in your head, move the decimal once and then cut it in half. So 6. Okay, 10% of 120 would be 12. So half of that would be 6. I feel like I'm gonna skip this one for right now. We can do it one more at the end if we need to, but let's move on and talk about a z-score. A z-score is simply a score that tells you how many standard deviations a data point is from the mean. So this is standard deviations from the mean. When a z-score is positive, the data point is above the mean. When it's negative, it's below the mean. When z is 0, the data value equals the mean. Okay. So to find a z-score, you want to know how far it is from the mean. So that would mean x minus the mean. And then you want to know how many standard deviations that is, so you're going to divide by the size of a standard deviation. I believe that formula is on your reference sheet. You find it on there? Okay. If you take AP Stats, you use z-scores a lot. We're not going to use it a ton because we're going to use our calculator on some of these. But it says, a radar detector records the speeds of a group of cars that pass by. If the mean is 46 and the standard deviation is 2.8, find the z-score for each data value. So if the mean is 46 and the standard deviation is 2.8, so this is our score, 52. So we would do 52 minus 46, that is 6 points above, and the standard deviation is 2.8. So how many standard deviations is that? It's roughly 2, but can someone tell me? Ugh. 2.1? Okay. 42 is going to be what kind of a number? Is it above or below? It's below. So we're going to find out how far below the mean is it, which is 4, and then we're going to divide by the mean of 2.8. Ugh. 1.4, negative 1.4, somebody? In AP Stats, do you usually round to the nearest tenth of a z-score? Don't know. Don't use them much, really? I thought you used z-scores a lot. I know Mr. Dredge did. I feel like there's better ways on the calculator now. But okay, 47 is really close to the mean, right, guys? 47 minus 46 over 2.8. Anybody got that one? 0.3? 0.36? I'm not gonna be picky about rounding. On the quiz, I think there's one question, just asked you to use the formula to find something. The mean number of total miles ran last week by each member of the track team was 4, so that's our mu value, with a standard deviation of 1.2. If Clay's z-score was 2.5, oh, so we know the z-score, we want to find x, how far he ran. So if we set that up, we'd have 2.5 equals x minus 4 over 1.2. Okay. We're in pre-calc. How do we solve that? Ben, what are you doing first? Okay, multiply, so we'd have 1.2 times 2.5. What did you get there, Ben? This came out 3? Is that exactly 3?
Yep.
Okay. My brain was not processing that. So then if we add 4 over there, we get 7. Okay, so he ran 7 miles. All right, so that was z-scores. I don't have a lot on z-scores. But when a value is not helpful to use the empirical rule, do you notice all of the values they gave us on these examples, all of these numbers, like they said 77, 72, and 87, those were numbers that were exactly on our little chart, right? Okay, what if it said, what is this, the people who scored 85 or above? Do you see that that's not on this? I can't break it down that fine at 85 using that empirical rule, where our calculator will do this for us. We are going to use the button called normal CDF, okay, combined probability, because we're going to give it a range of values. We're going to say the upper and lower limits, the mean and the standard deviation. And you can use z-scores. It defaults to 0 and 1 because you could use upper and lower z-scores, but I'm not going to do that because we can just put in the scores they ask. All right, so let's write down some information and then I'll show you on the calculator. The high temperature in Virginia Beach during the month of July are normally distributed with a mean of 83. I'm going to do a really rough little sketch here, and a standard deviation of 6. Find the probability that on any given day during the month the temperature is greater than 92. If I were to keep adding 6 here, do you see that 92 and above is somewhere in here? It's not hitting one of my nice little lines. Do you see what I'm talking about? Okay, so we'd have to get a decimal z-score and do some crazy business, but we can do this on our calculator by saying the normal combined, and then we're going to say the lower limit. If you have an older calculator, you have to put it in with commas. The upper limit, the mean, and the standard deviation, okay? Now, our calculator, if you have the nicer ones, will prompt you for all those things. What are we going to use for the lower limit for what we have put down here? What did I shade, guys? What's the lowest I want? 92. Okay, now the upper limit, we could go, a lot of teachers will say 4 standard deviations is the most you need to go, 5 standard deviations is the most. The calculator doesn't care. We could put in 9999 for the upper limit, okay? We just want everything over 92. So I just put some magical big number. You could put 110 degrees, it doesn't matter. And the mean was, what was it, guys? 83, and the standard deviation is 6. So let's try this. If we go second, VARS, remember, and it's number 2, near the top there. The PDF would give us what is the probability that it's exactly 92 or whatever it was, but we want 92 and over, so we're going to use a combined probability here. So 92, and you guys put whatever you want in there. I'm going to put 120 because you're going to show it's not going to matter. The mean was, I already forgot, was it 83 and 6? Okay. I got 0.0668. Did someone put in 0.99999? Did you get about 0.0668? Yeah. It doesn't matter as long as you go at least 3 or 4 standard deviations above, it won't make a difference. So I just usually use a big number. And somehow in my brain, putting nines is bigger than putting like 1, 0, 0, 0. I don't know why, but that's the way my brain works. Okay, because it's not true. But what did we get? 0.067 if we round to that. Okay, something like that. Or 6.7%. Was that what it was? Or 6 point? Yeah, 6.7%. I don't remember how Delta Math has you do those. Okay. The mean number of hours that an average person watches television per day is 4.18 hours with a standard deviation of 1.19. Find the probability that someone watches between 3 and 5 hours. Well, clearly, exactly 3 and exactly 5 aren't going to fall nicely on these weird decimal mean and standard deviation, right? So let's just do norm CDF because it's not nice. And what do we want to use for our lower limit? 3 hours, upper limit, 5, the mean, 4.18, and 1.19. Okay? Show you one more time. Second VARS, choice 2. We did 3, 5. Tell me if, was it 4.18 and 1.19? Was that the right one? Anybody have an older calculator and need help? Are you doing okay? So 59.4%. Now, or 0.59 if you round to 2. Yeah, I don't know how Delta Math. Okay, I did yeah. Okay, let's. What do I got left here? Is this the last one? Okay. The mean song length on Jack's iPad is 3 minutes and 3 seconds. Oh, this is like a converty one. With a standard deviation of 24 seconds, find the probability that the next song is no more than 3 minutes and 45 seconds. Should we do it all in seconds, guys? Since the standard deviation is 25 seconds or 24 seconds, I can read. What is 3 minutes and 3 seconds? 3 times 60 plus 3 would be 183 is the mean. Seconds. My S's look like 5, so I'll write seconds. Okay. Find the probability that we have a song less than 3 minutes and 40, so less than 3 times 60 plus 45. Is that 225? Okay. So how are we going to put that in? Sure. You could put negative 999 or something, but the shortest song would be 0, right? So that seems like a good lower limit to me. I agree. And the upper limit, we want 225 mean standard deviation. Somebody give me what you get. 0.96. Somebody else agreeing? Yeah. Okay. So about 96% probability that it will be 3 minutes and 45 seconds or less. No, you don't have to convert on the quiz, for sure. I just wanted to show you, okay, the homework is in Delta Math, okay? I was just gonna go back to this one real quick, this number 3 that we skipped. I wanna show you that we don't get exactly the answer if we use the calculator. It said, what percent of gas stations sell a gallon of gas for at least $2.17? So this was 205 and 4 cents. So that's 209, 213. Well, this is not a good example. 217. So it's above there. Minus 4 cents would be 201, 197. Here, let's do this. Okay, let me do this one with you. what probability that a gas station sells a gallon of gas for less than 197, so that would be all of these, or more than 205? Do we wish we had these gas prices, guys? Okay, using the empirical rule, how could we find that percent? Well, this half is how much? 50. And this, we could try to add those up, but it would be better probably to subtract from 100. Wasn't this 34 and 13.5? Do you have that on your sheet? So what is 100 minus 34 and 13.5? 68, 55, 54, 52.5. I can't even write a 5 today. 52.5%. All right. What if we wanted to use the calculator for that question? Is there a way to tell the norm CDF? Anybody have any ideas? Okay. What if we found the percent in between those two prices and then subtracted from 100? Isn't that what we did kind of in essence anyway? Okay, but let's put in the actual numbers. What were the prices? 197 to 205? And the mean was? Oh, the mean was 205? What was the upper, oh, that was the upper limit, okay. 205, where the mean was 205, sorry, I forgot. And the standard deviation was how much? 4 cents? Okay, so we get an answer of this, but we want the rest, right? So if we subtract that from 1, well, mine's gonna be negative, but we get 52.3%, okay? So we use the empirical rule because it's handy to be able to do things that fall on exact standard deviations. And it's something you can estimate without necessarily having a fancy calculator that does this. Does that make sense? This is considered more accurate, and mine only came out negative because I subtracted in the wrong order. So we got 52.5 using this little rounded rule, and it was 52.27 using the calculator, okay? Any questions? All right, delta math, I don't think there's very many. Does anybody, okay, let me stop.